Hey everyone, welcome to this electrifying course on C++ in finance and trading. Get ready to unlock the power of C++ as we explore how to build high-performance trading systems, implement machine learning techniques, and master algorithmic trading strategies. Along the way, you'll gain practical skills in developing robust financial applications, from trading algorithms to risk management tools. We have tons of coding exercises, hands-on examples, and valuable resources to enhance your learning experience, so don't forget to check out the GitHub repository linked in the description for all the code. If you love diving deep into finance and tech, hit that subscribe button. Now, let's get started. Party popper. C++ has played a significant role in this technological evolution, particularly in the realm of high-performance computing. Today, we're diving into how this powerful programming language is not just a staple of software development, but also a cornerstone in the financial industry. So, grab your calculators and prepare your eyes, because we're about to unravel the magic behind C++ in finance. In this code snippet, we implement a simple trading algorithm using C++. The trading algorithm class encapsulates the functionality required to evaluate market conditions and execute trades. The execute trade method is responsible for printing out a message indicating the purchase of a specified quantity of shares for a given stock at a certain price, showcasing how trading actions can be represented through functions. The core logic of this algorithm lies in the evaluate market condition method. Here, we compare the current market price to a target price. If the current price is below the target, the algorithm executes a trade by calling the execute trade method. This conditional structure reflects the fundamental principle of trading decisions based on price evaluations, which is central to algorithmic trading strategies. Finally, the main function serves as an entry point for the program, instantiating the trading algorithm class and invoking the evaluate market condition method with example prices. This structure allows students to grasp the essential concepts of condition-based trading and demonstrates how simple logic can form the building blocks of more complex financial algorithms. In this example, we delve into creating a simple market data processing system using C++. The market data processor class plays a pivotal role by managing a collection of stock price data. It utilizes a private vector to store incoming market prices, allowing for efficient data handling. The add data method is crucial as it appends new price entries to the vector, ensuring that our dataset remains up to date. Next, the calculate average function employs the SDD, accumulate algorithm to sum all price values stored in the vector. This method not only computes the total, but also calculates the average by dividing the sum by the total number of entries, giving traders insight into current market conditions. Lastly, the display market conditions function outputs the calculated average price to the console, providing immediate feedback to users. This structure allows for easy extension. For instance, traders could develop further functionalities to track trends or detect anomalies in real time. Overall, this code provides a foundational understanding of data processing in a trading context, showcasing how C++ can effectively manage and analyze market data. In this segment, we will explore a practical implementation of option pricing using the QuantLib library in C++. The code begins by setting a specific evaluation date for our calculations, which is crucial for pricing options accurately. The type of option, whether a call or a put, is defined alongside key parameters such as the strike price, underlying asset price, volatility, and risk-free interest rate. Next, we initiate a European option with the defined parameters, preparing it for pricing. The core of the pricing mechanism relies on the Black-Scholes process, whereby we set up the necessary market components, including the current asset price and interest rates. This is accomplished through handles that wrap the market data, enhancing performance and usability. Finally, we compute the option's net present value, NPV, which indicates its price based on these models, and print this value to the console. This demonstration not only illustrates how to leverage QuantLib for complex financial calculations, but also emphasizes the efficiency of C++ in executing performance-intensive tasks integral to trading systems. In this section, we will explore a simple implementation of a linear regression model in C++. The first key component of the code is the linear regression class, which encapsulates the functionality needed to train a model and make predictions. It has two private member variables, slope and intercept, essential for defining the linear equation. The train method accepts two vectors of historical stock prices, x and y, representing the data used for training. While this basic implementation simplifies the learning process by using preset values for slope and intercept, in practice, these would be dynamically computed based on the input data to best fit the trend. The predict method then uses the learned slope and intercept to extrapolate future prices based on the provided input. In the main function, we create an instance of the linear regression class and prepare some sample historical stock prices as vectors. After calling the train method with this data, we use the predict method to forecast the stock price for a specific future point. The output displays the predicted price, illustrating how C++ can effectively handle fundamental machine learning tasks relevant to finance. As we continue to advance toward a world dominated by data, the demand for skilled C++ developers in finance is only expected to grow. The powerful combination of performance, low latency capabilities, and real-time processing makes C++ indispensable. It empowers developers to create robust trading systems capable of meeting the fast-paced market's needs. In summary, the role of C++ in finance reaches far beyond basic programming. It is foundational to high-frequency trading, real-time data processing, and powering algorithmic systems that are reshaping the industry landscape. So, sharpen your C++ skills, because the financial future is fast, and it's only just getting started. As we look forward, trends like machine learning integration are set to revolutionize finance further, presenting ample opportunities for innovation and growth using C++. Grab your eye and dive into these applications, whether optimizing existing models or building entirely new systems. With a solid understanding of C++, the financial landscape could very well be your playground. To build high-performance financial trading systems, developers must possess a diverse skill set that spans multiple domains. This unique blend of skills includes not only programming proficiency, particularly in languages like C++, but also a solid foundation in finance, mathematics, and algorithmic design. Today, we'll explore the intricacies of building such systems, focusing on key areas such as architecture, performance optimization, and real-time data handling. So far, we learned that C++ is integral to high-performance computing, especially in finance, where it powers algorithmic trading and real-time data processing. Its speed and efficiency allow for high-frequency trading and robust financial analysis, making it a preferred language for developers in the industry. Leveraging libraries like Quantlib enhances C++ capabilities, enabling complex financial calculations and machine learning applications. As the demand for skilled C++ developers grows, its role in shaping the future of finance becomes increasingly vital. Now, we will talk about building high-performance trading systems. The ring buffer class is a fundamental building block for efficiently handling real-time market data in high-performance trading systems. This class uses a vector to store the market prices while keeping track of the head and tail indices to manage the circular nature of the buffer. When a new price is added, it locks the mutex to ensure thread safety and then updates the head index. If the head wraps around and equals the tail, it overwrites the oldest value, maintaining a consistent size for the buffer. The get method, which retrieves data from the buffer, also ensures thread safety with a mutex lock and throws an exception if the buffer is empty, allowing for effective error handling. Additionally, the isEmpty method provides a straightforward way to check if the buffer has any data currently available. This mechanism is crucial for real-time data handling since it prevents bottlenecks and race conditions, allowing the trading system to function smoothly under high-frequency trading scenarios. Overall, the classes and methods here illustrate how careful design and implementation in C++ can facilitate efficient data management in complex financial systems. In this section, we implement a simple trading strategy using a moving average crossover approach, encapsulated in our moving average class. This class maintains a vector of prices and a specified period, allowing us to add new prices and calculate the simple moving average. The addPrice method efficiently manages the size of the price list, ensuring it only retains the most recent values up to the defined period. The core of our trading logic resides within the trading strategy function, which continuously fetches data from the ring buffer. As new prices are obtained, both the short-term and long-term moving averages are updated. The function compares these averages to determine trading signals. A buy signal is generated when the short-term average exceeds the long-term average, and a sell signal when the opposite occurs. We also utilize an execute trade function that logs these trades, providing clear outputs whenever a buy or sell action is executed. This structure not only highlights the clarity and organization of our trading logic, but also exemplifies how C++'s performance capabilities enable real-time decision-making in trading environments. In this segment, we implement a basic risk management model designed to help traders determine the appropriate trade size based on their account balance and a specified risk factor. The Risk Manager class encapsulates two key attributes: account balance, representing the total funds in the trading account, and risk factor, which denotes the percentage of the account that can be risked on a single trade. The constructor initializes these properties, allowing for easy instantiation of the class with user-defined values. The primary method, calculate trade size, takes a stop-loss parameter, which signifies the maximum amount the trader is willing to lose on a trade. This method computes the trade size by multiplying the account balance by the risk factor and then dividing by the stop-loss amount. This calculation directly informs the trader about how many shares they can buy or sell, while adhering to their risk management strategy. By automating this assessment, the Risk Manager significantly aids traders in making informed, real-time decisions, essential in the fast-paced, high-frequency trading environment, where prompt execution can have a substantial impact on outcomes. In the following implementation, we focus on the order book class, which is central to our execution management system. This class utilizes a queue to efficiently handle pending orders, allowing for streamlined interaction with market APIs for executing trades. The place order method is responsible for queuing new orders by creating an order instance that holds the order ID, price, and the action, either buy or sell. When an order is placed, it gets stored at the back of the queue, enabling the system to maintain the order of execution. The execute order method is equally important, as it processes the orders in a first-in, first-out FIFO manner. If there are no pending orders, it promptly informs the user by printing a message. Otherwise, it retrieves the front order from the queue, removes it, and displays relevant information such as the order ID, action, and price executed. This straightforward management of order processing is vital for minimizing slippage and ensures that trades are executed at the intended price. directly reflecting the objectives of an efficient execution management system. In high-frequency trading, effective logging is essential for monitoring system performance and identifying issues. The logger class in this snippet is designed to facilitate the logging of messages by maintaining a connection to a specified log file. When an instance of logger is created, it attempts to open the file in append mode, meaning that new log entries will be added at the end, preserving any existing data. Should the log file fail to open, an error message is printed to the standard error stream. This serves as an immediate notification for any issues related to file accessibility. The constructor and destructor handle resource management, ensuring that the log file is properly closed when the logger object goes out of scope. The log method is the core functionality of this class, allowing users to write messages to the log file conveniently. When invoked, it checks if the log file is open before appending the message, ensuring that logging occurs without interruptions. This simple yet powerful logging mechanism enables traders and developers to capture critical insights into trading operations and system behavior, aiding in performance analysis and debugging efforts as they navigate the complexities of high-frequency trading systems. As we move forward, it's vital to emphasize that building a high-performance trading system is an iterative process. Testing and optimizing each component, market data handlers, trading engines, risk management, and execution systems, ensures that the entire system can respond promptly under high loads. By combining solid architectural design with efficient coding practices in C++, developers can leverage the language's speed and efficiency to create robust trading systems that meet the demands of today's financial markets. In conclusion, as we've discussed, building high-performance trading systems is a multidisciplinary challenge that requires a strong grasp of programming, financial principles, and mathematical concepts. By mastering these skills and utilizing the power of C++, you can create efficient, scalable, and reliable trading systems that not only perform well in theory, but also succeed in real-world applications. Keep digging into these approaches, and remember, each iteration you make is a step toward refining your trading system for better results. In this section, we will implement a decision tree classifier using Python's scikit-learn library to analyze historical financial data. We begin by loading the dataset, which contains crucial features such as income, age, and investment experience, along with a target variable indicating the success of investments. By separating these into two distinct sets, X for features and Y for the target, we prepare our data for analysis. Next, we utilize the train-test-split function to divide the data into training and testing sets, enhancing the model's reliability by ensuring we have unseen data for evaluation. We then instantiate a decision tree classifier and fit it to the training data, allowing the model to learn the relationships between the features and the target variable. Following training, we make predictions on the test set and evaluate our model's performance using accuracy metrics. This accuracy score not only reflects how well our model performs on the testing data, but also provides insights into its ability to categorize potential investment opportunities effectively. In our exploration of neural networks using TensorFlow, we'll implement a feed-forward neural network to predict stock prices. The first step involves loading the dataset from a CSV file, where we extract features such as technical indicators and the target variable indicating price change. To ensure our model trains effectively, we split the dataset into training and testing sets, with 70% for training and 30% reserved for evaluation. Next, we build a sequential model comprising 3 layers. The first 2 layers utilize 64 neurons each, activated by the rectified linear unit ReLU function. This architecture is advantageous for capturing nonlinear relationships within the data. The final layer is designed to output a single continuous value, suitable for regression tasks. We compile the model using the Atom Optimizer, which adjusts the learning rate during training, and set the loss function to mean squared error, a common choice for regression problems. After creating the model, we proceed to train it for 100 epochs with a batch size of 32, monitoring validation performance through a split of the training data. Finally, we evaluate the model on the testing set, providing a test loss value that reflects the model's predictive accuracy on unseen data. This process equips us with insights into the neural network's performance in predicting stock price movements. In our implementation of support vector machines, SVM, for stock price movement classification, we begin by importing necessary libraries, including pandas for data manipulation, train test split for dataset splitting, SVC for creating the SVM model, and metrics for assessing model performance. After reading the dataset from a CSV file, we segregate the features, which are indicators of stock movement, from the target variable that represents whether the stock's price will increase or decrease. Subsequently, we split the data into training and testing sets, allocating 30% of the data for testing to ensure that our model evaluates its performance on unseen data. We then instantiate the SVM classifier with a radial basis function kernel, enabling it to handle nonlinear relationships in the data effectively. Once the model is trained on the historical stock data, it is used to make predictions on the test set. Finally, we calculate and print the accuracy score, which helps us quantify how well the SVM predicts stock prices, providing valuable insights into its effectiveness in a financial context. As we evaluate these algorithms, the next natural question arises: how do we choose the right one for our specific task? The selection depends on several factors, including data size, feature types, and the kind of prediction or classification one aims to achieve. Typically, decision trees are a good starting point due to their interpretability, especially in finance, as they can be understood and explained to stakeholders easily. However, as datasets grow larger and more complex, neural networks often offer enhanced capabilities, allowing them to learn intricate relationships without needing extensive feature engineering. They can capture nonlinear patterns that traditional models might miss, providing an edge for high-frequency and algorithmic trading strategies. On the other hand, SVMs shine when we're dealing with smaller datasets with well-defined boundaries, thus ensuring effective classification tasks. To effectively evaluate our decision tree model, we can implement k-fold cross-validation, a technique that allows for a more reliable assessment of performance. In this code, we begin by importing the necessary function, cross-val_score, from the Sclern model selection module. We first initialize an instance of the decision tree classifier, which will be our model for prediction. By calling cross-val_score, we then apply k-fold cross-validation, specifying a parameter, CV equals 5, which divides our dataset into 5 distinct subsets or folds. The model is trained and validated 5 times, each time utilizing a different fold as the test set while using the remaining folds for training. This process helps ensure that every data point gets evaluated, providing a more comprehensive picture of the model's accuracy. After executing the cross-validation, the code computes and prints the accuracy scores for each fold, followed by the mean accuracy across all folds. This user-friendly output not only highlights the model's performance consistency, but also serves as a crucial insight into its reliability, helping to mitigate overfitting risks and guiding further model tuning for better results. In this section, we focus on feature selection, a crucial process that can significantly enhance the performance of our predictive models. We begin by importing the necessary components from the Sclern library, specifically the recursive feature elimination, RFE method, and logistic regression model. Next, we establish a base model using logistic regression, which is particularly suitable for binary classifications. We then create an RFE model specifying that we want to select the top 3 features from our dataset. RFE works by recursively removing the least important features until only the specified number is left, ensuring that the remaining features contribute the most to model accuracy. After fitting the RFE model to our dataset, we retrieve 3 key outputs: The first indicates the number of features selected, confirming whether we've focused our analysis correctly. The second output reveals which features were deemed most valuable, indicated by a Boolean array. Lastly, we obtain the feature ranking, allowing us to see how each feature scores in importance relative to the others. This systematic approach to feature selection improves model efficiency, crucial when working with larger financial datasets. Lastly, let's touch on the importance of keeping abreast of the latest techniques. Machine learning is a rapidly evolving field, and new advancements emerge regularly. Tools like reinforcement learning are gaining traction in financial markets, allowing systems to learn optimal trading policies based on single or multiple objectives. It's influential not only for automated trading strategies, but also for managing risk dynamically. Continued learning through resources such as online courses, research papers, and participation in communities will keep practitioners in finance at the forefront of innovation, maintaining a competitive edge in a rapidly advancing technological landscape. As we wrap up this exploration of implementing machine learning techniques in finance, remember that the application of algorithms goes beyond just selecting one. A deep understanding of the data and continuous refinement of models is vital to achieving success in financial markets. Harnessing the power of decision trees, neural networks, and support vector machines provides financial analysts with powerful tools for making data-driven, informed decisions. The practical experience you acquire through coding and model implementation can serve as the foundation for continual growth and adaptation in this dynamic field. Keep experimenting, learning, and pushing boundaries as you journey forth in this exciting blend of finance and technology. In the world of finance and trading, building a high-performance, low-latency system is critical for success. This overview will guide you through the intricacies of financial trading systems. We will cover everything from the architecture and design principles to specific technologies and methodologies that not only enhance performance, but also ensure reliability and scalability. So far, we learned about how machine learning techniques can significantly enhance trading strategies and risk management in finance. We focused on components like decision trees, neural networks, and support vector machines. We've explored implementations using Python libraries such as scikit-learn and TensorFlow, while emphasizing the importance of feature selection and model evaluation. The iterative nature of model building fosters continuous testing and optimization, enabling professionals to extract insights from large datasets and make informed predictions. As the field evolves, staying updated with the latest advancements is crucial for maintaining a competitive edge. Now, we will cover the key components and design considerations critical for financial trading systems. The trading system class forms the core of our low-latency trading architecture, integrating essential components such as the market data handler, order management system, and execution system. In the initializer, we instantiate each of these components, establishing a clear structure for our trading system. The run method employs an infinite loop where it continuously fetches market data using the market data handler. Here's where the decision-making process comes into play. We apply logic, specifically within the make decision method, to determine whether to place an order based on the received market data. If a decision is made, the system interacts with the order management system to place the order and subsequently calls the execution system to carry out the order. This separation of concerns is crucial as it keeps the code maintainable and scalable. The make decision method is currently a placeholder for the algorithm that will analyze market conditions, allowing for future enhancements. Overall, this design exemplifies a modular approach, paving the way for easy updates and adaptations as trading strategies evolve. This structure not only ensures efficiency, but also sets a strong foundation for further development and optimization in trading systems. In this segment, we will explore a key component of our trading system, the market data handler, which is essential for receiving real-time market information. The market data handler class initiates a socket connection to a specified host and pot, enabling the system to connect to a market data feed, typically using protocols like FIX. Once a connection is established, the handler continuously retrieves data by calling the getMarketData method, which listens for incoming market updates. The data is received in raw form and then parsed into a structured format through the parseData method, ensuring that other components can quickly and accurately utilize the information for trading decisions. Although the actual parsing logic is not implemented here, it's crucial as it converts low-level data into more usable forms that traders can act upon. The efficiency of this component is vital, as timely updates can significantly impact trading strategies and decisions. This setup encapsulates the core functionality needed to manage incoming market data effectively, forming the backbone of our trading architecture. In this section, we will explore the structure and functionalities of the Order Management System, OMS, implemented in the provided code. The code defines a class called Order Management System that plays a crucial role in handling and routing orders within a trading environment. Upon initialization, it creates an empty list called OrderBook to store active orders. The placeOrder method is responsible for accepting new order details. It first validates the order using the validateOrder method, which currently serves as a placeholder but represents an essential function for ensuring that the order meets specific criteria, such as quantity and price correctness. If the order is valid, it is appended to the OrderBook, and the routeOrder method is called to determine where to send the order for execution, although the details of this routing logic are yet to be implemented. By incorporating methods for validation and routing, this OMS structure sets up a foundation that can be expanded with additional features like logging order statuses or imposing penalties for late executions, making it adaptable to the complexities of financial trading systems. The execution system is a pivotal component that directly engages with financial exchanges to carry out order placements effectively. In our implementation, the class execution system features a method called executeOrder, which is designed to handle the transmission of an order to a specified market venue. While the actual logic for connecting to an exchange and executing the order remains unimplemented, indicated by the placeholder POS. It is crucial to envision how this method will be equipped to manage various trading requirements, including interfacing with multiple venues and adhering to time constraints for order execution. In practical applications, this method should incorporate mechanisms to ensure orders are processed promptly and accurately, reflecting the operational demands of high-frequency trading. The underlying idea is to optimize performance and maintain low latency, which is essential in a fast-paced financial environment. Properly implementing this system would involve handling order states, such as fills or cancellations, making it robust enough to deal with the dynamic nature of financial markets. Thus, understanding the significance of this code helps shed light on how trading strategies are realized through efficient execution mechanisms. In this section, we delve into a crucial aspect of system performance by simulating network latency using a simple function in Python. The core functionality of this code is encapsulated in the simulate network latency function, which introduces a controlled delay to emulate the potential network latency encountered in real-world trading applications. By utilizing the time sleep 0:001 command, we create a 1 millisecond pause. This tiny delay serves as a tool for developers to better understand and assess how the trading algorithms would perform under conditions that mimic actual data transmission delays. Although a 1 millisecond gap may seem trivial in high-frequency trading environments, such delays can accumulate significantly, impacting overall performance. This function is particularly useful to test and develop strategies that are sensitive to latency, allowing developers to evaluate their system's responsiveness. By running simulations with adjusted latency settings, they can identify bottlenecks and optimize their trading logic, ensuring decisions are made as swiftly as possible when market opportunities arise. Understanding and addressing these principles is vital for enhancing the performance of financial trading systems. In this section, we focus on configuring high-performance network interface cards, NICs, for kernel bypassing, which is essential for minimizing latency in trading systems. The setupNIC function serves as a placeholder for the necessary configuration actions required to enable kernel bypass. By bypassing the operating system kernel, applications can directly access NIC hardware, significantly decreasing the processing overhead associated with traditional data handling through the kernel. This direct access is crucial in financial systems, where every millisecond counts and the volume of data can be immense. To implement this configuration effectively, developers might use specialized libraries like Solaflayer's OpenOnLoad, which are optimized specifically for such performance enhancements. The function indicates where these configuration actions would be applied, ensuring that the NIC is primed for high-speed data transmission. By leveraging tailored hardware configurations and incorporating kernel bypass techniques, trading systems can achieve the necessary speed and efficiency needed to process market data in real time, thereby maintaining a competitive edge in a fast-paced financial environment. The monitoring system is essential for maintaining the performance of trading applications. In the class definition, we see the monitoring system, which serves as a base for implementing logging and performance tracking functionalities. The log event method is designed to capture and store various performance metrics, such as latency and auto statuses. Although the logging implementation is currently a placeholder, it is crucial for identifying performance issues as they occur. By continuously logging events, the system ensures that valuable operational data is readily available for analysis, enabling proactive maintenance. Additionally, the monitor latency method indicates a pathway for measuring the system's internal latency. This method would typically involve mechanisms to assess the time taken for different processes and communications within the trading framework. Monitoring latency is vital, as even minor delays can significantly impact trading efficiency and decision-making. Overall, this monitoring class emphasizes the importance of real-time analytics in trading systems, offering a foundation for further enhancements that could include more sophisticated performance metrics and alerts. In conclusion, building a high-performance, low-latency financial trading system requires a deep understanding of the design principles, continuous integration of best practices for both software and hardware design, and agile responses to ever-evolving market dynamics. By effectively utilizing components like market data handlers, order management systems, and execution engines, coupled with strategies for latency minimization, traders are better prepared to navigate the complex waters of modern financial markets. As we continue this journey, remember that every microsecond can lead to a significant change in the trading landscape. Keeping your systems optimized, up-to-date, and ready to adapt is the cornerstone of trading success. The beauty of design patterns lies in their proven track record and the common language they offer to developers. Understanding design patterns is essential for creating robust, maintainable, and scalable software systems. In this video, we'll explore various design patterns in system architecture, their benefits, and how to implement them effectively. So far, we learned about the critical architecture of financial trading systems, emphasizing low-latency performance and reliability. We discussed essential components like market data handlers, order management systems, and execution systems, along with strategies to minimize latency and enhance system performance. Now we will cover design patterns, an important aspect of developing efficient and effective system architectures. Design patterns are typical solutions to common problems in software design. They serve as templates that can be customized to solve specific issues in your codebase. Rather than reinventing the wheel, developers can apply these tried-and-tested patterns, saving time and reducing errors. The use of design patterns promotes code reusability and makes communication among team members easier, as patterns introduce a common vocabulary in development discussions. In essence, design patterns streamline the development process, providing clear structures for building applications. In this section, we delve into the singleton design pattern, which ensures that a class has only one instance while providing a global access point to it. The singleton class defined in the code employs the new method to control the instantiation process. Initially, the instance class variable is set to none. Within the new method, a check is performed to see if an instance of singleton already exists. If it does not, a new instance is created using super, and instance is assigned this newly created object. If an instance already exists, the method simply returns the existing instance, guaranteeing that any call to create a singleton object will yield the same instance. Additionally, the SumBusinessLogic method offers a placeholder for implementing functionality relevant to the singleton, emphasizing that this pattern is not just about instance control, but also about defining behavior that can be accessed uniformly. By integrating the singleton pattern into our trading system, we ensure consistent management of shared resources, such as database connections, which is crucial for maintaining performance and reliability in our system architecture. In this section, we explore the factory method pattern through the implementation of a trading strategy system. The core of the design involves an abstract class, trading strategy, which mandates that all derived classes implement the execute method, promoting a consistent interface for different strategies. We then create two concrete strategy classes, market order strategy and limit order strategy. Each of these classes implements the execute method to define its specific behavior when a trading action is executed, thus encapsulating the details of how each trade is carried out. The strategy factory class plays a pivotal role in this design by providing a static method, createStrategy, which accepts a strategy type parameter. This method decouples the instantiation of strategy objects from the client code, allowing the client to remain unaware of which concrete class it will receive. Instead of directly instantiating the strategies, the client simply calls this factory method. This approach adheres to the open-closed principle, making the system extensible. By introducing new trading strategies in the future, we can enhance functionality without modifying existing code, thereby promoting maintainability and scalability in our trading system architecture. In this segment, we'll dive into the observer pattern, which allows for a dynamic response to changes in state within a system. Here, we have a subject class that serves as the central point of notification. It stores a list of observers in an internal list and provides methods to attach, detach, and notify these observers. When the market data changes, the notify method is invoked, iterating through the observers list and calling the update method on each observer, effectively broadcasting the new data to all registered observers. The trading strategy class implements the observer interface, specifically the update method, which is responsible for processing the incoming market data notification. In our example, when notified, the trading strategy will print a message indicating it has been updated with the latest data. By encapsulating the observer behavior, this design promotes the flexibility of the trading system. Strategies can independently register or deregister as observers, reacting to market fluctuations without coupling with other system components. This decoupling enhances maintainability and promotes a scalable architecture, crucial for complex systems like financial trading platforms. In this section, we will explore the strategy pattern through the implementation of a trade execution system. The code begins with an abstract class, trade execution strategy, which defines a method execute. This enforces that any specific trading strategy must implement this method, ensuring that all derived classes provide their own execution logic. Two concrete strategies are then created. Best price execution, which implements the execute method to indicate executing a trade at the best available market price, and iceberg order execution, which suggests using an iceberg order method for trading. This separation of strategies allows for distinct algorithms suitable for varying market conditions. The trade context class acts as a context in which these strategies operate. It initializes with a chosen strategy and provides a setStrategy method, enabling the client to modify the strategy dynamically at runtime. The execute trade method leverages the currently set strategy to perform the trade execution, encapsulating the logic behind the chosen algorithm. This design enhances the flexibility of the trading system, allowing it to adapt to evolving market conditions seamlessly by changing its execution strategy without altering the core trading logic. In this section, we explore the implementation of the command pattern within a trading system. The command class serves as the abstract base class, establishing a structure for concrete command implementations. It defines an abstract method, execute, which must be overridden by subclasses to define specific command behavior. The byCommand and cellCommand classes inherit from command, each encapsulating a stock transaction. When an instance of either class is created, it takes the stock symbol as an argument, which it uses in its overridden execute method to return a string indicating the respective action. The command invoker class plays a pivotal role in this pattern. It maintains a list of commands, providing methods to add commands to this list and execute them in sequence. Upon execution, each command's execute method is called, producing a response for each transaction. Importantly, once the commands are executed, the list is cleared, emphasizing the one-time nature of these operations. This entire structure allows for flexible management of stock transactions, including the potential for extending functionality to support undue operations or batch processing in a complex trading application. In this section, we are implementing the adapter pattern, which facilitates the integration of incompatible interfaces within a trading system. Here, we have two distinct classes, Legacy Trading API and Modern Trading API. The Legacy Trading API class provides a method to place an order, while the Modern Trading API class sends orders in a different format. To bridge this gap, we create the Trading Adapter class, which takes an instance of Legacy Trading API as an argument. It provides a unified method, placeOrder, that allows us to call the Legacy API's placeOrder method seamlessly. This design enables us to utilize existing legacy functionalities without altering the original implementation, promoting code reusability and flexibility. When using the adapter, we first instantiate the Legacy Trading API, followed by creating a Trading Adapter object that references the Legacy API. This allows us to invoke the placeOrder method on our adapter, seamlessly integrating with the legacy system. This approach demonstrates how to effectively manage legacy code and modern systems, enhancing maintainability and supporting smooth transitions in evolving architectures. The decorator pattern is a powerful design pattern that enhances the behavior of objects dynamically. In this implementation, we start with a basic trading strategy class that executes a simple trading strategy. The strategy decorator class serves as a base class for other decorators, allowing them to extend the functionality of any trading strategy passed to them while maintaining the same interface. The logging decorator introduces logging capabilities, modifying the execute method to append a message indicating that logging is enabled. This allows us to track actions without altering the original strategy's logic. Similarly, the risk management decorator builds upon the logging functionality, adding risk management features to the strategy. By combining decorators, we can layer responsibilities seamlessly, effectively evolving our trading strategy's capabilities. This pattern provides great flexibility in managing trading strategies by allowing us to add new features at runtime without changing existing code. Thus, decorators enable easier enhancement of functionality, making your trading systems more adaptable to varying requirements and improving code maintainability. In conclusion, design patterns represent a treasure trove of ready-made solutions for common issues in software development. Each pattern, from singleton to decorator, helps structure code in a way that emphasizes maintainability, scalability, and flexibility. These patterns facilitate better communication among developers as they introduce a shared vocabulary and method of structuring solutions. Understanding these design patterns is crucial for anyone aspiring to write efficient, clear, and manageable code, particularly in complex fields like financial trading systems. As you continue to build your skills in software architecture, remember these patterns. They're your toolkit for creating robust applications that can adapt to the ever-changing demands of the market. With a solid grasp of these concepts, you're now equipped to tackle more complex architectural challenges. The knowledge of design patterns will aid you in making sound architectural decisions, ensuring your systems are both scalable and maintainable. Happy coding! The financial world moves at a breakneck speed, generating and consuming massive volumes of data each second. This intense flow of data not only necessitates the use of high-performance computing systems, but also shapes the very landscape of how we process, analyze, and utilize information. In today's session, we will delve into the realm of high-performance computing, HPC, uncovering its significance, components, and applications, particularly in sectors such as finance and scientific research. So far, we learned about the significance of design patterns in software development, emphasizing their role in creating robust and maintainable systems. We explored various design patterns such as singleton, factory method, observer, strategy, command, adapter, and decorator, which enhance code reusability and overall system flexibility. Now we will cover high-performance computing, its architecture, and how to effectively leverage it in real-world applications. High-performance computing can be visualized as a sophisticated orchestration of hardware and software designed to perform complex calculations at unprecedented speeds. Central to this is the parallel processing capability, where multiple processes or cores work simultaneously to solve problems. This is in stark contrast to traditional computing, where tasks are executed sequentially, leading to bottlenecks in performance. By distributing workloads across several processing units, HPC can significantly reduce the time taken to analyze vast datasets or execute intricate simulations. Consider a financial institution conducting a risk assessment for thousands of investment portfolios. Using traditional computing, processing this data could take hours or even days. However, employing a high-performance computing system allows them to perform these calculations in minutes, providing actionable insights more rapidly. In this example, we utilize Python's multiprocessing module to demonstrate how parallel processing can significantly speed up the calculation of the sum of a large array of numbers. We begin by defining a function, calculateSum, which takes a list of numbers as input and returns their sum. This function will be executed concurrently across multiple processes. In the main block of the program, we first generate a large array containing 1 million random numbers. To effectively utilize multiple CPU cores, we define the number of processes to be used, in this case, foo. Using a context manager, we create a pool of worker processes. The large array is divided into smaller chunks, each corresponding to a process. By mapping the calculateSum function to these chunks, we enable simultaneous computation, allowing each process to calculate the sum of its assigned portion of the array. Finally, we aggregate the results from all processes by summing the individual sums from each chunk, thereby yielding the total sum of the array. This not only illustrates the power of parallel processing, but also showcases how high-performance computing can enhance performance for data-centric tasks. In this example, we utilize the message passing interface, MPI, to showcase how parallel processing can be achieved across multiple nodes in a high-performance computing environment. The code begins by importing the necessary libraries, MPI4Pi for MPI functionalities and NumPy for numerical operations. We then establish a communication context with MPICOMMWorld, which allows all processes to communicate with each other. Each process identifies its unique rank and the total number of processes, which is crucial for managing data distribution. The root process, indicated by rank 0, initializes a dataset with random numbers, while all other processes set their data to none. To distribute this data across processes, we employ the scatter method, which sends chunks of data to each process, enabling them to work simultaneously. Each process computes its local sum of the received data using NumPy. After all processes have calculated their local sums, the results are aggregated through the reduce function, which sums all local results and returns the total to the root process. Finally, the root process prints the total sum, demonstrating how effectively MPI facilitates collaboration among nodes, enhancing computational efficiency in handling large datasets. In this section, we simulate a simple job scheduling system to illustrate the concept of resource management within high-performance computing (HPC) environments. The code begins with the definition of a job scheduler class, which encapsulates all functionalities related to job queuing and processing. Inside this class, we initialize an empty list called job queue to hold the tasks that will be scheduled. The addJob method allows us to append new jobs to this queue, showcasing the flexibility of adding diverse computational tasks. The call function, runJobs, processes these tasks in the order they were added, ensuring that the first job to enter the queue is the first one to be executed. This mimics a first-in, first-out FIFO scheduling mechanism often found in real HPC job schedulers. As each job is executed, the system displays a message indicating which job is currently running. While this implementation is basic, it effectively highlights the essence of job scheduling in HPC, emphasizing the need for orderly and efficient job management to optimize resource usage. In practical scenarios, such systems would incorporate more sophisticated features for prioritization and resource allocation based on the specific demands of various computational tasks. In this segment, we utilize TensorFlow and Python's multiprocessing capabilities to efficiently train a neural network model on a large simulated dataset. First, we generate a dataset comprising random features and labels, which provides a foundation for our model training. The createModel function constructs a simple sequential neural network with a hidden layer, utilizing RayLU activation for the hidden layer and compiling it with the Atom optimizer and mean squared error loss function for regression tasks. The trainModel function is where the training of our model occurs. It initializes a new model instance and fits it to a provided subset of the dataset for a fixed number of epochs. To take advantage of parallel processing, we split the dataset into smaller chunks corresponding to the number of worker processes specified. Each chunk will be handled independently, enhancing training efficiency. By employing the multiprocessing library, we create a pool of worker processes that concurrently invoke the trainModel function on the various data chunks. This parallel training approach significantly reduces the overall training time, showcasing the power of high-performance computing in the realm of machine learning. In this section, we explore how to calculate the expected return of a portfolio using NumPy, which is an optimized library ideal for linear algebra operations. First, we simulate random returns for 4 assets over 1,000 time periods, creating a matrix where each row represents a time period and each column represents a different asset. This approach allows us to analyze large datasets efficiently. Next, we compute the mean return for each asset by using NP, mean, which simplifies the process of obtaining average returns across the columns of the matrix. Furthermore, we calculate the covariance matrix with NP, cov, which provides insight into how the asset returns move together, a critical element in risk assessment and portfolio management. We then define equal weights for each of the 4 assets, which is a common practice in portfolio theory when no specific weighting strategy is applied. The expected portfolio return is calculated using NP dot, which performs a dot product of the mean returns and the weights, yielding a single number that represents the portfolio's expected return. Finally, we print the expected return along with the covariance matrix, offering a succinct overview of both the anticipated performance and the risk profile of the investment portfolio. As we wrap up our discussion, it is clear that high-performance computing is not just a luxury, but a necessity in our data-driven world. From finance to scientific research, the ability to process and analyze vast amounts of data quickly and efficiently can drive innovation and provide a competitive edge. Understanding the architecture, the components involved, and how to leverage these tools will empower you to navigate the exciting challenges and opportunities that HPC presents. So far, we covered the essential aspects of high-performance computing, including its architecture, parallel processing, resource management, job scheduling, and applications in data analytics and machine learning. As you explore further into this field, remember that the pursuit of efficiency, speed, and computational prowess will open new doors and elevate your capabilities in technology and beyond. As you continue to learn about high-performance computing, consider hands-on experimentation, optimization, and exploring advanced architectures. The possibilities are vast, and the applications are just as exciting as the technology itself. Thank you for joining me today, and I look forward to diving deeper into HPC and its myriad applications in future lessons. Choosing the right data structure for implementing a limit order book, LOB, can significantly impact its efficiency and performance. Data structures are essential in organizing and managing data effectively, especially in high-frequency trading environments where speed is crucial. In this session, we will dive into various data structures that are primarily used in financial systems and explore strategies that leverage these structures for optimal performance. So far, we learned about the significance of high-performance computing, HPC, in processing large datasets quickly and efficiently, highlighting its importance in sectors like finance and scientific research. We explore the architecture of HPC systems, including parallel processing, resource management, and job scheduling, which enhance computational capabilities. Additionally, we discuss the applications of HPC in data analytics and machine learning, demonstrating how optimized algorithms and libraries can improve performance. Lastly, we emphasize the value of hands-on experimentation and optimization to fully leverage HPC's potential. Now we will cover data structures and strategies specifically suited for financial systems. The price history class provides a mechanism to efficiently track a fixed number of stock prices in a circular manner. In the init method, we initialize the object with a specified size, creating an array to hold the prices and setting the current index to 0. This setup allows for constant memory usage, as our price history will always maintain the same amount of storage regardless of the number of prices added. When new prices are recorded using the addPrice method, the current price replaces the price at the position indicated by the index modulo the size of the array. This wrapping mechanism ensures that once we reach the end of the array, it continues from the start, effectively overwriting older prices while keeping the latest entries readily accessible. The getHistory method returns the complete list of prices stored in the array, allowing users to review the tracked history. This implementation effectively illustrates the use of arrays to maintain a fixed size for storing essential data in financial applications, although it also hints at the limitations in flexibility that come with such a structure. In this section, we introduce a simple implementation of a linked list to manage transactions dynamically. The core component of our structure is the node class, which represents each transaction. Each node holds two elements, the transaction data and a reference to the next node, allowing for continuous linking as new transactions are added. The transaction list class manages the linked list itself. It initializes with a head attribute set to none, indicating that it starts off empty. To add new transactions, the addTransaction method creates a new node containing the supplied transaction data. This new node becomes the new head of the list, with its next pointer pointing to the previous head, ensuring efficient O1 insertions. Lastly, the printTransactions method loops through the list starting from the head, accessing each node's data and printing it sequentially. This forward traversal demonstrates how linked lists maintain their order and allows for straightforward retrieval of all transaction data. While this approach offers flexibility in managing transactions, it is essential to remember that access time may be slower for sequential searches compared to other data structures. In this section, we explore the implementation of a binary search tree, BST, specifically designed to manage stock prices efficiently. The treeNode class represents each node in the tree, holding a price value alongside references to its left and right child nodes, allowing for structured traversal. The priceBST class defines the core functionality of the BST. It begins with an initializer that sets the root to none. The insert method is crucial, functioning to place new price entries into the tree. If the tree is empty, it creates the root node. Otherwise, it calls a private recursive method, insertrec, to find the correct position for the new price based on its value. This approach ensures that prices are organized in ascending order, aiding swift retrieval. The search method utilizes a similar recursive technique implemented in sertrec, which navigates through the tree to determine if a specific price exists. This structure not only facilitates efficient insertion and searching, operating in logarithmic time complexity, but also maintains sorted data, making it ideal for applications in financial systems such as order books and asset management. In this section, we explore the order and order book classes, which leverage the efficiency of hash tables for managing orders in a financial application. The order class is a simple representation of an order, consisting of two attributes: ordered, which uniquely identifies the order, and amount, which indicates the value of the order. The order book class manages these orders using a dictionary, or hash table, enabling rapid access and modifications. When a new order is added through the addOrder method, the order is stored in the dictionary with the ordered as the key and an instance of the order class as the value. This structure allows for quick retrieval of order details through the getOrder method, which uses the get function of the dictionary to access details based on the order ID. If the order exists, its details are returned. If not, a message indicating that the order was not found is provided. This efficient approach is particularly crucial in high-frequency trading scenarios, where speed and quick access to order information are paramount for effective decision-making. The min-heap implementation provides an effective way to manage priority in data handling, particularly useful in trading systems where access to the minimum or maximum value is essential. It begins by importing the heap module, which allows us to leverage an efficient heap queue algorithm. The min-heap class is defined with an initializer that sets up an empty list to store the heap's elements. The insert method enables the addition of new values, which are automatically arranged in a way that the smallest element can be accessed easily, thanks to the heapush function. To access the minimum value, the getMin method checks if the heap is not empty and returns the first element, ensuring efficient access to critical values. For situations where it is necessary to remove the smallest element, the extractMin method pops this element from the heap while handling cases where the heap might be empty. This structure is particularly beneficial for managing orders that need to be prioritized, ensuring that the most critical operations are performed in a timely manner, a crucial aspect in high-frequency trading. In this section, we focus on implementing a simple queue to manage trades, which operates under the first in first out FIFO principle, mirroring real-world order execution. The trade queue class begins with an initialization method that creates an empty list to hold trades. This list will dynamically adjust as trades are added or removed. The inQueue method allows us to add new trades to the back of the queue, ensuring that they are processed in the order they arrive. This is critical for maintaining the integrity of the trade processing sequence. Conversely, the dequeue method removes and returns the trade from the front of the queue. If the queue is empty, it responds with a message indicating that there are no trades to process. This provides a safeguard against errors when attempting to access non-existent trades. Additionally, the peek method allows users to view the trade that is next in line for processing without removing it from the queue, which can be useful for monitoring active trades. Overall, the trade queue class encapsulates the essential operations required for orderly trade management, making it a valuable tool in financial systems. When implementing these data structures, designers must consider their individual strengths and weaknesses. The choice of data structure directly affects the Big O notation of the algorithms involved, impacting overall system performance. High-frequency trading systems, for example, thrive on rapid data access and mutation. Hence, the use of efficient data structures is essential. In finance, efficiency is often synonymous with profitability. A well-chosen data structure can minimize latency, expediting the processing of trades and enhancing the user experience, giving firms a competitive edge in the markets. As you work on constructing financial applications, consider not just which data structures you will use, but also how they interact with your algorithms and data management strategies. In conclusion, understanding data structures is fundamental in crafting efficient algorithms for financial systems. From arrays and linked lists to trees and hash tables, each has particular scenarios where it excels. The trade-off between memory considerations, access speeds, and complexity should guide your choice for optimal results. As we wrap up today's discussion, remember that your selection of data structures informs how quickly you can retrieve data and how efficiently you can manipulate it, directly translating into the performance and reliability of your financial systems. In our next session, we will dive even deeper into algorithms tailored for financial applications, enhancing your toolkit further. Thank you for joining this exploration of data structures in finance. In the rapidly evolving landscape of financial trading systems, technology and innovation have consistently been at the forefront, driving transformations that redefine traditional paradigms. Within this domain, machine learning emerges as a pivotal force, revolutionizing how trading strategies and decisions are formulated. Today, we'll dive deep into how machine learning is reshaping the world of trading. We'll cover the significance of ML, its applications, algorithms, and even take a look at code examples that illustrate its power. So far, we've learned about the importance of selecting appropriate data structures for financial systems, focusing on arrays, linked lists, balanced binary search trees, hash tables, heaps, and queues, and explored how these structures impact efficiency in data access and manipulation, crucial for high-frequency trading applications. In our current lesson, we will discuss the transformative potential of machine learning in trading. To understand the significance of machine learning in trading, let's first consider the overwhelming amount of data generated in financial markets. Every tick, transaction, and market order contributes to a vast ocean of data that can be challenging to navigate. Traditional statistical methods often struggle under the weight of this complexity. Enter machine learning, which aims to decipher intricate patterns and adapt in real time as new data flows in. This allows for more informed predictions, which can significantly enhance trading strategies. Machine learning not only processes historical data, but also harnesses new information from alternative sources, like social media sentiment and geopolitical events. This capability is particularly beneficial for traders seeking to gain a competitive edge. Imagine a system that can analyze tweets about a company and gauge market sentiment, then compare that with historical trading patterns to determine the best time to buy or sell. The implications are profound, and that's just scratching the surface. In this section, we will implement a basic linear regression model to predict future stock prices based on historical data. First, we import the necessary libraries, which include NumPy for numerical operations, Pandas for data manipulation, scikit-learn for building the regression model, and matplotlib for plotting our results. We start by creating a sample dataset that captures daily stock prices over a specific period. This data is organized into a Pandas data frame, where we convert the date column to a data time format and set it as the index for better time series analysis. Next, we prepare the data for the model. The independent variable x is created by reshaping an array representing the number of days since the first observation, while the dependent variable y consists of the stock prices available in the data frame. After preparing the data, we instantiate a linear regression model and train it using the historical prices. With the model fitted, we can forecast prices for the next 5 days by generating future day indices, which provide us with predictions that we can plot alongside historical prices. Finally, we visualize the results with a line chart, highlighting the predicted prices in contrast to the historical data, illustrating how the model can help traders make informed decisions. In this section, we will explore a simple trading environment created using a class in Python, which simulates basic buy and sell functionality for an agent in a stock trading scenario. The trading environment class initializes with a specified balance and sets the starting stock price while tracking the amount of stock owned by the agent. Within this class, the buy stock method allows the agent to purchase stocks, provided it has enough balance to cover the transaction. Conversely, the sell stock method enables the agent to sell any stock it owns, updating the balance accordingly. The step method is crucial as it simulates market dynamics by randomizing price movements. Depending on the action taken by the agent, whether to buy or sell, this method invokes the respective functions to modify the agent's balance and stock holdings. This high-level abstraction not only demonstrates the agent's interaction with market prices, but also allows us to evaluate the effectiveness of various trading strategies over a set number of trading steps. By running simulations, students can analyze and refine their trading decisions, providing insights into the algorithmic trading process. In this section, we will explore a simplified implementation of a neural network using TensorFlow to predict stock volatility based on historical price data. The first step involves importing the necessary libraries, primarily TensorFlow and its layers module. We then create a sample dataset of historical prices, which serves as our input data. Subsequently, we prepare the features and target values for the model. Here, the feature set consists of the previous day's prices, while the target value is the change in price from one day to the next, enabling the model to learn the dynamics of market volatility. Next, we define a feed-forward neural network with one hidden layer. The hidden layer consists of 8 neurons, utilizing the RayLU activation function, which helps capture nonlinear relationships. The output layer produces a single value, representing the predicted price change. After compiling the model with the Atom Optimizer and mean squared error loss function, we proceed to train it using the historical data for 50 epochs. Finally, the trained model makes a prediction for the next day's volatility, providing insight that traders can utilize to make informed decisions about their positions and risk management strategies. By continuously retraining the model with new data, the system adapts to evolving market conditions, enhancing its predictive capabilities. As we have now explored various aspects of machine learning in financial trading, it becomes clear that its influence is extensive, touching every facet from predictive analytics to risk management and execution optimization. The algorithms we discussed, including linear regression, reinforcement learning, and neural networks, demonstrate that machine learning is not merely a theoretical concept, but a practical toolkit for real-world trading applications. It's important to note, however, that while ML can significantly enhance trading strategies, the quality of data remains paramount. The phrase garbage in, garbage out rings especially true. Ensuring data integrity and relevance is essential for the robustness of machine learning models, particularly in a volatile market where any inaccuracies can lead to substantial losses. In conclusion, the integration of machine learning into financial trading represents a paradigmatic shift. As we continue to navigate this evolving landscape, understanding and harnessing this technology will be vital for traders and institutions seeking to thrive in competitive markets. By embracing innovative methodologies and being willing to adapt, we position ourselves at the forefront of the future of trading. Thank you for joining me in this exploration of machine learning in trading. I hope you now appreciate the complexities and the immense possibilities that lie within this rapidly advancing field. Until next time, happy trading. Let's explore the methodology that we are going to use when implementing machine learning strategies for financial trading. Today, we are diving into the nuanced world of machine learning implementations, where we'll break down essential steps, discuss various methodologies, and provide practical coding examples to solidify your understanding. So far, we learned about the transformative power of machine learning in financial trading, focusing on its ability to analyze vast datasets and improve trading strategies through predictive analytics. We explored various algorithms and techniques, such as linear regression and reinforcement learning, which facilitate better decision-making in trading environments. Additionally, we discussed the significance of maintaining data quality to ensure the effectiveness of machine learning models. Now, we will cover the concrete steps and methodologies for implementing machine learning in trading systems. In this section, we will implement a foundational step for gathering historical stock data using the iFinance library. First, we define the stock ticker symbol for Apple Inc., AAPL, and specify the start and end dates for our data collection, pinpointing the period we want to analyze. The if download function is then employed to retrieve historical price data for our specified ticker within the given timeframe, effectively fetching it into a structured data frame. This data frame contains essential information such as opening, closing, high, and low prices, along with trading volumes, all of which are crucial for further analysis. By using the head function at the end of this process, we can display the first few rows of the dataset, allowing us to inspect its structure and ensure that the data has been correctly downloaded. This is a vital practice as it helps us familiarize ourselves with the data we will be working with in subsequent steps, establishing a solid foundation for our machine learning model. Remember, installing the iFinance package beforehand is essential to avoid any import errors. In this section, we will focus on preprocessing our dataset and extracting meaningful features that can enhance the performance of our machine learning model. First, we check for any missing values in the dataset, crucial for ensuring data integrity. By identifying these missing values, we can take appropriate actions to rectify them, which is done through interpolation, helping us fill in gaps with estimated values based on existing data. It's essential that we also convert the index of our data frame into a data time object to accurately facilitate time series analysis, allowing us to harness temporal trends efficiently. Once our data is clean, we proceed to feature engineering, which is vital in financial predictions. Here, we calculate the simple moving averages, SMA, for the closing price, specifically the 30-day and 100-day SMAs. These moving averages are significant indicators in technical analysis, providing insights into price trends over time. We then visualize the closing prices alongside these SMAs using Matplotlib. This plot serves as a clear representation of how these averages react to price movements, allowing us to analyze market behavior graphically. In this section, we implement a simple linear regression model using scikit-learn to forecast future stock prices. We begin by preparing the feature set and target variable. Specifically, we utilize the 30-day and 100-day simple moving averages, SMA, as our predictors and the closing price as the target variable. It's important to note that we only consider the data from the 101st row onward to avoid inaccuracies due to the initial rolling calculations of SMA. Next, we split our dataset into training and testing sets using the train-test-split function. This is crucial for evaluating the model's performance, as it ensures that the model learns from one subset of the data while being tested against another, unseen subset. Afterward, we instantiate the linear regression model and fit it to our training data, which allows the model to learn the relationship between our predictors and the target variable. Finally, we generate predictions on the test dataset. This phase is pivotal, as the accuracy of these predictions will inform us of the model's effectiveness and guide further improvements, such as exploring various evaluation metrics to assess model performance in greater detail. To evaluate the performance of our linear regression model, we calculate two important metrics: mean absolute error, MAE, and root mean squared error, RMSE. The mean absolute error provides a straightforward way to assess the average magnitude of prediction errors, offering insights into the typical deviation of our model's predictions from actual values, regardless of direction. By utilizing scikit-learn, mean absolute error, we pass our test set's true values and the predictions to get this metric. On the other hand, the root mean squared error emphasizes larger errors by squaring the individual differences before averaging them. This is particularly useful in scenarios where bigger discrepancies are more consequential. The mean squared error function allows us to compute this metric, with the squared equals false argument ensuring that we receive the RMSE instead of the mean squared error itself. Finally, we print both errors to facilitate model assessment. If either metric shows a high value, it may indicate that the model is underperforming, suggesting the need for possible adjustments in model complexity, feature selection, or data preprocessing efforts. In this section, we focus on the implementation of our trading signals based on the moving average crossover strategy. First, we initialize a new column called Signal in our dataset, setting its default value to 0, indicating no active trade. Starting from the 30th index onward, we use numpy's NP, a function to generate by signals, set to 1 when the 30-day simple moving average SMA exceeds the 100-day SMA, which indicates a bullish trend. The position column is then created to capture the changes in signal, highlighting where the buy 1 and sell -1 events occur through the diff method, allowing us to track transitions between buying and selling. Next, we visualize these trading signals on a price plot of Apple Inc. AAPL stock. The plot includes the closing price, with green triangles indicating the points of buy signals and red inverted triangles marking sell signals. This graphical representation helps us to easily identify where our trading strategy suggests entering or exiting positions. By equipping ourselves with these visual cues, traders can make informed decisions aligned with predicted market movements, fostering a more intuitive trading experience. Now, it's important to note the significance of continuous improvement in our machine learning journey. Once deployed, our model is not static. It requires continuous monitoring, evaluation, and refinement. Financial markets are dynamic, so models that worked well yesterday might not be performing effectively today. Implementing a feedback loop will help you adapt your strategy based on new data and changing market conditions. This can involve retraining your model periodically with new data or reevaluating your model's performance regularly to update the trading logic. In conclusion, implementing machine learning for financial trading is both an art and a science. From defining a clear problem statement to collecting and preprocessing data, building and evaluating models, and finally deploying strategies, every step is essential in creating a robust trading system. The methodologies we explored provide a foundational framework as we navigate this intricate landscape. As you embark on your journey into machine learning for trading, remember that practice and experimentation are key. By continually refining your approach and expanding your knowledge, you'll not only develop more effective strategies, but also become more adept at adapting to exciting changes in the financial markets. So grab your data, code away, and let the algorithms work their magic. Happy trading. So far, we learned about the methodology for implementing machine learning strategies in financial trading, focusing on defining clear problem statements and the importance of data collection and preprocessing. We discussed feature engineering, including the calculation of moving averages, and implemented a linear regression model to predict stock prices. Additionally, we covered the evaluation of the model using metrics like mean absolute error and root mean squared error, and explored creating trading signals based on moving average crossovers. Finally, we emphasized the need for continuous improvement and adaptation in trading strategies to keep up with dynamic market conditions. Now, we will cover the scalability of financial trading systems, exploring how they can effectively manage increased workloads and complexity. Scalability is not just a buzzword in modern finance, it's a necessity. As trading environments evolve, fueled by the rapid increase in transaction volumes and the complexity of data, financial systems must be designed with scalability in mind from the outset. The implementation of distributed systems in financial trading is a complex but necessary evolution to cope with the demands of modern finance. In this section, we will dive into the specifics of how scalable systems function and look into practical implementations to enhance the performance of trading systems. To begin with, let's define what we mean by scalability in the context of financial trading systems. Scalability refers to the system's ability to handle growth, whether that means an increase in transaction volume, the number of users, or the complexity of the trading algorithms being employed. In a financial trading scenario, if the system cannot scale adequately, it may lead to slow processing times, increased latency, and ultimately financial losses. Thus, the goal is to create a system that can expand its capacity without sacrificing performance. In this code, we implement a simple yet effective load balancer to manage incoming trade orders across multiple server instances. The load balancer class maintains a list of active servers and an index to track which server should process the next incoming order. When an order is routed, it checks if there are available servers, and if so, it selects one using a round-robin approach, which ensures each server gets an equal share of the workload. This design prevents any single server from becoming a bottleneck, thereby enhancing the system's scalability and resilience. The server class represents individual server instances, each capable of processing orders. When a server processes an order, it simply prints a message indicating it has handled the order, demonstrating its functionality. In the main section of the code, we initialize the load balancer and add 3 server instances to it. Finally, we simulate incoming orders by invoking the root order method on the load balancer in a loop. This basic implementation illustrates how horizontal scaling can be achieved, enabling the system to handle multiple orders concurrently and maintain operational efficiency. In this section, we implement a publish-subscribe model for market data processing. The Market Data Publisher class is designed to manage multiple subscribers who are interested in receiving updates about market data. When an instance of this publisher is created, it initializes an empty list for storing subscribers. The subscribe method allows new subscribers to join the publishers list, enabling them to receive data updates. The key functionality here is the publish data method, which takes a data input and iteratively calls the update method on each subscriber in the list. This ensures that every subscriber gets the latest market data as soon as it's published. On the subscriber side, the Market Data Subscriber class includes an update method that simply prints the received market data update. This design gives each subscriber the independence to handle data updates as they arrive, fostering system responsiveness and flexibility. The example usage demonstrates how to create a publisher and multiple subscribers, register them, and finally publish a market data update. This architecture helps maintain a robust and efficient system where data dissemination is timely and scalable, aligning well with the goals of high-performance financial trading systems. In this segment, we will explore a basic implementation of a transaction and ledger system that demonstrates the principles behind distributed ledger technology. The transaction class is designed to encapsulate the attributes of a trade, including the sender, receiver, and amount. It includes a validation method that checks if the transaction amount is greater than 0, ensuring that only valid transactions are processed. This foundational check is crucial for maintaining the integrity of transactions within the ledger. The ledger class serves as a container for these transactions, maintaining a chain of verified transactions. When adding a new transaction, the ledger calls the validation method from the transaction class to confirm its legitimacy. If the transaction is valid, it appends the transaction to its chain and notifies users with a confirmation message. Otherwise, it alerts that the transaction is invalid. At the end of the code, we create instances of transaction to simulate a trading environment and demonstrate how to manage incoming transactions in a very simplified financial ledger. This structure emphasizes the secure and tamper-proof characteristics of distributed ledgers, which are vital for reducing fraud and enhancing trust in trading operations. In this section, we introduce a simple implementation of a consensus algorithm, which is essential for maintaining data integrity across distributed nodes in a trading system. The class consensus algorithm is designed to handle leader election and transaction replication. When instantiated, it initializes a leader variable to none, which will eventually hold the elected leader's identifier. The method electLeader takes a list of nodes as input and assigns leadership to the first node in that list, printing a message to confirm the elected leader's identity. This simplistic approach serves as a foundational example. In practical applications, more sophisticated leader election methods would be employed to account for node failures or network partitions. Following leader election, the method replicate transaction allows the elected leader to manage the execution of trading transactions, ensuring that all nodes follow a consistent state. When invoked with a transaction, it prints a message indicating that the leader is replicating that specific transaction. This approach highlights how consensus mechanisms can help in maintaining order integrity within trading operations, balancing the need for consistency with the challenges posed by distributed architectures. We've covered numerous strategies and techniques for ensuring scalability in financial trading systems. These components, ranging from effective load balancing, data distribution, the utilization of distributed ledger technologies, to sophisticated consensus mechanisms, combine to create a robust framework capable of adapting to the rapid changes in the financial landscape. As we continue to enhance our trading system to accommodate future demands, we must remember that scalability is a complex journey and requires consistent evaluation and optimization. By combining sound architectural principles with the right technical implementations, trading systems can achieve not only the performance metrics demanded by today's markets, but also ensure their viability and robustness in the long term. In conclusion, the scalability of financial trading systems is not merely about coping with increased demand. It is about building a flexible, resilient framework that can thrive against the dynamic challenges of the fast-paced financial world. In this code, we implement an asynchronous approach to fetching market data from multiple financial symbols, highlighting the performance benefits essential in trading systems. The fetch market data function simulates the retrieval of market data for a specific symbol by introducing a random delay to mimic the time it might take for an actual network call. By doing so, we can test the efficiency of our implementation under realistic conditions. The process data function constructs a list of tasks that call fetch market data for each symbol simultaneously, demonstrating the power of Asyncio to handle multiple concurrent operations. Using Asyncio, gather, we can initiate these asynchronous tasks and wait for all of them to complete, resulting in a collection of market data that is retrieved in a non-blocking manner. This significantly enhances the responsiveness of our trading system, as waiting on each individual request would otherwise lead to increased latency. Finally, the main function orchestrates this process, calling process data and printing the retrieved market data, thus showcasing a clear and efficient way to manage multiple data feeds, a critical capability in high-frequency trading environments. In this section, we explore the implementation of a caching mechanism for stock price retrieval using Python's functools, LIU-cache. This decorator optimizes the getStockPrice function by storing results of expensive operations, allowing quick access to previously fetched stock prices. The function simulates a time-consuming database query by introducing a 2-second delay whenever a price is requested for a stock symbol that hasn't been cached yet. When you call the function with a symbol for the first time, it will take about 2 seconds to return the price, mimicking the expected delay when querying a live database. However, subsequent requests for the same symbol return instantaneously from the cache, illustrating the benefit of this caching strategy. The maximum size of the cache is set to 128 entries, which means that it can hold the most recent 128 stock prices before it starts evicting the least recently used ones. By using caching effectively, this approach reduces server load and response times, ultimately improving the performance of financial trading systems where timely data access is critical. In this section, we explore the implementation of an efficient sorting algorithm using Python's built-in sorted function, which is particularly effective for handling transaction records in financial systems. The code begins by simulating a list of timestamps generated randomly. This mimics real-world transaction data that would typically require processing. To evaluate the efficiency of the sorting operation, the code captures the start time prior to sorting and the end time after sorting is completed, allowing us to compute the total time taken for the sorting operation. By leveraging the sorted function, which employs timsort internally, the code reduces the computational complexity compared to simpler algorithms like bubble sort, resulting in faster performance. After the sorting operation, the elapsed time is printed, providing insight into how quickly the sorting occurs. This optimization is crucial in trading systems, as quicker sorting translates to better responsiveness and enables timely decision-making when executing trades. Overall, this example underscores the importance of selecting efficient algorithms to maintain high performance in processing large datasets, ensuring that trading systems can effectively manage real-time data. In this code snippet, we leverage Python's concurrent futures module to efficiently handle trade executions using a thread pool. The execute trade function simulates the trade execution process, intentionally introducing a delay to mimic the time taken in a real scenario. This setup is crucial for understanding how to manage multiple concurrent trading tasks without overwhelming system resources. We create a list of trade orders, which includes both buying and selling actions for different stocks. By utilizing the thread pool executor with a maximum of 2 concurrent threads, we maintain control over the number of simultaneous executions. This approach ensures that, regardless of the number of orders, our system remains balanced and responsive, preventing resource saturation. After dispatching the trade orders, we gather the results by mapping the execute trade function across the orders. This results in efficient handling of multiple trades, allowing for optimal use of CPU resources. Finally, by printing the results of each executed trade, we can verify that our system successfully processes trades within the established parameters. This method not only highlights the effective use of concurrency, but also serves as a foundation for scaling trading systems in a high-performance environment. In this segment, we focus on profiling live systems to identify performance bottlenecks. The code utilizes Python's built-in cprofile module, a valuable tool for analyzing where time is spent during program execution. The primary function defined is main operations, which simulates a repetitive task with a loop that prints a message multiple times. This straightforward approach allows us to assess the overall performance of the function when it is executed. By invoking cprofile run on the main operations function, we gather data about execution time for each function call within it. The output of cprofile will provide detailed statistics, including the time spent in each function, the number of calls made, and the cumulative time taken. This information is essential for developers looking to optimize their code, as it highlights which areas are slow and may benefit from improvement. Using such profiling tools is crucial in high-performance environments like trading systems, where understanding and enhancing the execution efficiency of functions can lead to significant performance gains. In this section, we focus on the importance of optimizing database interactions in high-performance systems, particularly in the context of financial trading. The SQL command presented here creates an index on the symbol column of the trades table, using the command create index IDEX symbol ON trades symbol. Indexes are crucial in databases as they allow for faster retrieval of records by creating a structured reference to the data, reducing the time it takes to locate specific entries during query execution. By indexing the symbol column, the database can quickly find trades associated with any given symbol, significantly decreasing the response time for queries that involve looking up symbols. This can dramatically enhance performance, especially in environments like high-frequency trading, where milliseconds can make a difference in transaction efficiency. As you design your trading systems, remember that effective database indexing strategies can alleviate potential bottlenecks, ensuring that your system remains responsive even as transaction volumes increase. This technique is a fundamental approach to maintaining high performance in your financial applications. In summary, achieving high performance in financial trading systems requires a blend of strategies that encompass efficient data processing, caching, algorithm optimization, resource management, monitoring, and smart database interactions. Implementing these approaches helps to ensure that your trading system can not only scale effectively, but also operates with the responsiveness and agility necessary to thrive in fast-moving markets. Now, as you continue your journey in building advanced trading systems, remember that performance isn't just a nice-to-have. It's a critical factor that can determine success in trading. Keep experimenting, coding, and refining your techniques, and get ready to conquer the world of trading with high-performance systems. Understanding low-latency programming is crucial, especially in contexts like financial trading systems. This method of programming focuses on minimizing delays in code execution, enabling applications to respond rapidly to incoming data and user interactions. In today's lesson, we'll explore key principles and techniques essential for low-latency programming in C++, a fundamental component in creating high-performance financial systems. So far, we've learned about the importance of strategic scalability in financial trading systems, focusing on efficient data processing and performance optimization. We explored techniques like asynchronous data handling and caching to enhance responsiveness and reduce latency. Additionally, we discussed algorithm optimization, effective resource allocation through worker pools, and the significance of monitoring and profiling systems for performance enhancement. Finally, we emphasized smart database interactions, such as indexing, to ensure that high-frequency trading systems can operate effectively in dynamic market environments. Now, we'll dive into the realm of low-latency programming, specifically how it can be leveraged in C++ to enhance the performance of financial applications. In this section of the tutorial, we will examine two simple functions designed to process integer and floating-point values, highlighting the differences in their efficiency due to how the CPU handles these data types. The process_integer function takes an integer input, squares it, and then outputs the result. This operation benefits from the CPU's ability to perform integer arithmetic quickly due to their straightforward binary representation and less complex processing requirements. In contrast, the process_float function processes a floating-point number in a similar manner, but the nature of floating-point arithmetic involves more complex calculations, which can introduce latency. When executed within the main function, both processing functions are called with their respective data types, 10 for integer processing and 10.5 for floating-point processing. By contrasting these functions, we underscore a key principle in low-latency programming. Prefer integers over floating-point numbers when possible to reduce execution time and optimize performance, an insight particularly valuable in high-frequency trading systems where every millisecond matters. This example emphasizes the impact of data types not just on performance, but also on the design choices made by developers in performance-critical applications. In this section, we illustrate the impact of data access patterns on cache performance using a matrix example. The code begins with a definition of a two-dimensional matrix of size 1000 by 1000. The initializeMatrix function fills this matrix with the sum of its indices. This simple operation demonstrates the need for efficient data initialization before we analyze access patterns. The crux of cache optimization comes into play with the access matrix row-wise and access matrix column-wise functions. The row-wise approach accesses the matrix sequentially based on rows, leveraging the row major storage order used by C++. This method incurs fewer cache misses, resulting in faster execution times. Conversely, the column-wise access method leads to scattered memory access, resulting in more cache misses and slower performance. Highlighting the commented out lines in main, students can experiment with both access methods to observe the tangible differences in performance. By comprehending these concepts, programmers can harness cache-friendly coding strategies fundamental to high-frequency trading systems, where every microsecond counts. In low-latency programming, implementing an effective warm-up routine is crucial for optimizing system performance before actual operations begin. The warm-up routine in the code is designed to prepare the CPU by executing a set of dummy calculations, which helps to fill the CPU cache with relevant data. By performing these calculations in a loop, the routine ensures that the CPU is primed and ready for the upcoming high-frequency tasks, minimizing execution delays. In this specific implementation, a simple loop runs 10,000 iterations where a volatile integer, temp, is assigned the square of the loop index. Declaring the variable as volatile is essential because it prevents the compiler from optimizing away this computation, ensuring that the CPU performs all iterations fully. Following the warm-up, the main function calls this routine, thereby setting the stage for subsequent trading algorithms to run more efficiently. By invoking this warm-up routine, developers not only enhance immediate performance, but also lay the groundwork for smoother operation during critical trading activities. This practice can significantly reduce latency, making it particularly beneficial in the fast-paced world of financial trading systems. In this segment, we'll explore how batching operations can significantly reduce system call overhead, enhancing performance in time-sensitive applications. The code defines a function, batch write to disk, which takes a vector of strings as input. Within this function, a single string buffer is constructed where all the elements from the vector are concatenated, each followed by a newline character. This approach effectively gathers multiple writes into one operation, instead of executing separate write calls for each string. The write function is then used to send the entire buffer's content to the standard output in one go, which minimizes the context switching overhead typically associated with individual system calls. This is particularly beneficial in scenarios like logging or communications where rapid data handling is required. In the main function, a sample vector of trade data is created, and the batch write to disk function is called, showcasing the practicality of this batching technique. By reducing the number of system calls, not only do we streamline the operation, but we also enhance the overall responsiveness of the application, a key objective in low-latency programming. In this section, we'll examine a fundamental example of how branch prediction can optimize performance in low-latency programming. The code begins by defining the process data function, which takes an integer input and checks if it exceeds 100. Based on this condition, it outputs whether the input is classified as high or low. This simple structure allows the CPU's branch predictor to make educated guesses about the likely path of execution, particularly when the input is consistently high due to historical patterns. Within the main function, a loop processes 1 million iterations by passing integers from 0 to 999,999 into process data. Here, you can observe the critical importance of organizing conditional checks to favor the more frequent outcome. If most inputs are expected to be below 100, the current organization may lead to mispredictions, increasing latency. Therefore, a thoughtful arrangement of conditionals tailored to expected input distributions can effectively enhance CPU performance by reducing branch misprediction penalties, ultimately facilitating smoother execution flows in high-frequency trading systems where latency is vital. In this section, we explore a simple yet effective example of measuring execution time in C++ using high-resolution clock features from the Chrono library. The sample function demonstrates a basic workload, executing a loop 1 million times without any internal calculations, serving primarily as a performance benchmark. In the main function, we employ SDD, Chrono, high-resolution clock to capture precise start and end timestamps surrounding the execution of sample function. By subtracting the start time from the end time, we obtain the execution duration, which is then displayed in nanoseconds. This technique is paramount for profiling performance, allowing developers to identify slow functions and spot areas ripe for optimization. Using profiling and benchmarking tools alongside, such code provides valuable insights into function call times and memory usage, making it easier to analyze and enhance code efficiency. This foundational concept is essential in low-latency programming, especially in high-performance applications like financial systems, where even minor optimizations can lead to significant improvements in execution speed. As we reach the conclusion of this exploration into low-latency programming, it's evident that various techniques intertwine to provide optimal performance in financial systems. Understanding CPU architecture, implementing cache-friendly coding practices, minimizing kernel interactions, incorporating effective warm-up routines, and utilizing profiling tools are essential strategies for achieving low latency. The development of high-performance algorithms requires meticulous attention to how code behaves at the hardware level. In upcoming lessons, we'll dive deeper into advanced C++ optimization techniques, exploring newer features and tools that continue to push the boundaries of programming speed and efficiency. By applying these strategies, developers can significantly improve the performance of financial systems, positioning themselves to meet the evolving challenges in fast-paced markets. Thank you for joining this lesson on low-latency programming, and I hope you're excited to implement these techniques in your own projects. In today's tutorial, we dive into advanced optimization techniques in C++, focusing on how to enhance your program's performance. This session is packed with useful strategies that can make a difference, especially when developing high-performance applications like financial trading systems. So far, we learned about the critical aspects of low-latency programming, particularly in financial trading systems. We covered the importance of understanding hardware-software interaction, optimizing code execution through data types and cache performance, and minimizing kernel interactions for enhanced efficiency. Additionally, we explored strategies like system warm-up and branch prediction to reduce execution delays. Finally, we highlighted the role of profiling tools in identifying performance bottlenecks and optimizing algorithms for superior outcomes in fast-paced markets. Now, we will cover advanced C++ optimization techniques, specifically regarding floating-point operations, inline functions, compile-time polymorphism, modern C++ features, and effective use of compiler optimization flags. In this part of the tutorial, we will explore a practical example that demonstrates the performance differences between floating-point and integer arithmetic in C++. The code defines two functions, compute with float and compute with int. In compute with float, we initialize a floating-point variable result to 0 and then enter a loop that runs from 1 to 10 million. During each iteration, we perform a floating-point division by incrementing the result with the inverse of the loop index, showcasing the typically more computationally intensive nature of floating-point operations. The result is then printed to the console, providing a precise value. Alternatively, the compute with int function employs integer arithmetic by initializing a long variable and summing integer values, again through a loop running up to 10 million. This integer-based approach is less computationally demanding compared to floating-point calculations. The main function measures the execution time for both operations using high-resolution clock functions. This side-by-side comparison clearly illustrates the performance implications of using floating-point versus integer arithmetic, reinforcing the earlier discussion on optimization in high-performance contexts like financial systems. Through this example, students can see the tangible impact of choosing different data types on execution speed. In the following example, we explore the concept of inline functions in C++. The code begins with the inclusion of the IAStream library, which allows us to perform input and output operations. We define an inline function named square, which takes an integer parameter x and returns its square by multiplying x by itself. By declaring this function as inline, we notify the compiler to substitute calls to square directly with its definition during compilation, thereby minimizing the call overhead associated with traditional function calls. In the main function, we declare an integer variable num and initialize it to 10. We then utilize the std count to display the result of squaring num by calling the inline function square num. This call gets replaced by the expression num at compile time, leading to faster execution. It's essential to use inline functions for small, frequently invoked operations, as this technique enhances performance while optimizing memory usage, despite the potential for increased binary size. Thus, this snippet effectively illustrates the benefits and usage of inline functions within performance-critical C++ applications. In this section, we delve into the concept of compile-time polymorphism using C++ templates, which enables us to create flexible and reusable functions tailored for different data types. The code showcases a simple yet powerful template function called add, which accepts two parameters of the same type and returns their sum. By declaring the function template with the syntax template typename t, we allow the function to operate on any data type, whether it's an integer, float, or another supported type. When we invoke add57, the compiler deduces that t should be of type int, generating an appropriate version of the function specifically for integer addition. Similarly, calling add57.3 prompts the compiler to create a separate version for floating point calculations. This demonstrates how templates facilitate type safety without compromising performance, as the necessary code is generated at compile time, ensuring that type-specific implementations are used during execution. Ultimately, this approach not only enhances code maintainability, but also leads to efficient execution, a crucial aspect in performance-driven applications. In this section, we will explore how to implement compile-time calculations using the constexpa feature in modern C++. The code defines a function called factorial, which computes the factorial of a given integer n. By utilizing constexpa, this function enables the compiler to evaluate the factorial value at compile time instead of runtime. This optimization can lead to a significant reduction in execution time, particularly when the function calls are frequent, such as in performance-critical loops. In the main function, we declare a constexpa variable named result that stores the factorial of 5. Thanks to constexpa, the compiler computes this value during the compilation process, meaning that result is ready to be used immediately without any delay. The final line outputs the computed factorial, providing instant feedback to the user. This method not only sharpens performance by minimizing runtime calculations, but also demonstrates how modern C++ features can lead to more efficient and streamlined coding practices. In this part of our tutorial, we'll explore how compiler optimization flags can significantly enhance the performance of your C++ programs. The command we are using is meant to compile a program file with the O3 optimization flag, which invokes the compiler to apply aggressive optimization techniques during the build process. This level of optimization enables features such as function inlining, which can eliminate the overhead of function calls by embedding function code directly at call sites. Additionally, O3 performs loop unrolling, allowing multiple iterations of a loop to be executed in a single cycle, which can minimize the loop control overhead. Vectorization is another key feature, enhancing performance by enabling parallel execution of operations on data arrays, thereby making better use of modern CPU architectures. It is essential to note that while these optimizations can substantially improve execution speed, profiling your application before and after applying such flags is vital. By measuring performances, you'll gain insights into how your specific code behaves under different optimization levels, ensuring that you also avoid potential pitfalls like compiler-induced bugs. Finally, it's essential to connect all these advanced optimization techniques with profiling and benchmarking. No matter how much optimization you apply, nothing beats having solid performance data. Utilizing profiling tools like gprof, perf, or valgrind can offer insights into where your program spends the most time, which functions are bottlenecks, or if there are memory usage spikes that could be optimized. For instance, providing feedback based on profiling data can enhance and tweak performance optimally. Once you understand where bottlenecks lie, you can focus your optimization efforts effectively, be it through implementing inline functions, better type management, or compiler flags. In conclusion, mastering advanced C++ optimization techniques is a journey into understanding both the language's capabilities and your application's needs. These tools in your programming arsenal can drastically improve the performance of your software, particularly in demanding environments like financial trading systems. Keep pushing the boundaries with these techniques, revisit the fundamentals of performance, and as always, profile, test, and refine. Thank you for joining today, and remember that the performance landscape is always evolving, so keep learning and optimizing. The advent of blockchain technology and its application in cryptocurrencies has transformed financial systems worldwide, redefining how we think about digital transactions, trust, and value exchange. In this tutorial, we will explore the foundational aspects of blockchain technology, the integral role cryptocurrencies play in this landscape, smart contracts, decentralized finance, DeFi, and the intricacies of developing blockchain applications. This lesson aims to provide a comprehensive understanding of how blockchain challenges traditional financial paradigms, while offering new avenues for innovation, efficiency, and security in financial transactions. So far, we've learned about advanced optimization techniques in C++ to enhance program performance, particularly for high-performance applications like financial trading systems. Now, we will cover blockchain technology and cryptocurrencies, exploring their definitions, functionalities, and influence on the financial world. In this section, we delve into the fundamental structure of a blockchain block through a block class defined in Python. Each instance of the block class represents a single block in the blockchain, encapsulating essential information such as its position in the chain index, a reference to the hash of the previous block, a collection of transactions it contains, and a timestamp indicating when it was created. The init method initializes these attributes, ensuring that every block maintains a unique identity within the chain. Importantly, upon initialization, the block also computes its own hash through the calculateHash method. This method takes a snapshot of the block's current state by converting its attributes into a JSON string format, which is then hashed using the SHA-256 algorithm. This process emphasizes the fundamental principles of blockchain technology: immutability and transparency. Any modifications to the block's data would alter its hash, thus preserving the integrity of the blockchain. Overall, this class lays the groundwork for understanding how blocks function and interact within the broader blockchain framework, key concepts in the realm of cryptocurrencies and decentralized transactions. In this section, we will examine a fundamental pseudocode example that demonstrates how transactions work within cryptocurrencies. The function, sendTransaction, serves as the core of the transaction process, ensuring that funds are transferred securely and efficiently. The function begins by checking whether the sender has sufficient balance to complete the transaction. If the sender's balance meets or exceeds the specified amount, the function proceeds to deduct that amount from the sender's account. This step is crucial for maintaining the integrity of the balance, as it prevents overspending and ensures that the sender can meet their obligations. Following this, the amount is credited to the receiver's account, effectively completing the transfer. Once the transaction is successfully executed, the function broadcasts this new transaction to the network. Broadcasting is vital in a decentralized environment, as it ensures all nodes have consistent data, thus upholding the transparency and security of the blockchain. If the sender does not possess enough funds, the function returns a message indicating an insufficient balance, providing clear feedback on the transaction status. This simple yet effective logic encapsulates the principles of security and decentralization foundational to cryptocurrency transactions. The liquidity pool class is a fundamental component for managing liquidity in decentralized finance, DeFi applications. At its core, this class provides the functionality to add and remove liquidity for specified tokens, which is crucial for facilitating transactions on decentralized exchanges. When a new liquidity pool instance is created, it initializes with an empty dictionary called pool. This dictionary will store the available liquidity for different tokens, where the token name serves as the key and the corresponding amount of liquidity serves as the value. The addLiquidity method allows users to increase the liquidity of a specified token. It checks the existing amount of that token in the pool and increments it by the amount specified, effectively allowing users to contribute their assets to the liquidity pool. Conversely, the removeLiquidity method enables users to withdraw liquidity. It ensures that the token exists in the pool and that the amount to be removed does not exceed the available balance. If both conditions are satisfied, the specified amount is deducted from the pool, making it accessible for users to reclaim their funds. This functionality empowers users to actively manage their investments within the DeFi ecosystem. In this segment, we will delve into the functionality of a trading bot designed to respond to market signals. The core function, named Trading Bot, takes in market data as an argument. It analyzes the market data for a specific signal that dictates trading actions. If the signal indicates a buy action, the bot executes a buy order through the function executeBuyOrder. This action is crucial for taking advantage of favorable market conditions when the price of a cryptocurrency may rise. Conversely, if the signal indicates a sell action, the bot triggers executeSellOrder. This feature is essential for locking in profits or minimizing losses when the market shows signs of decline. The simplicity of this pseudocode illustrates the foundational logic behind automated trading strategies, enabling traders to react swiftly to market changes without human intervention. This automation helps manage time-sensitive trades more effectively, allowing traders to capitalize on the high volatility of the cryptocurrency markets. By employing such strategies, traders can enhance their efficiency and precision, an indispensable advantage in the dynamic landscape of cryptocurrency trading. In conclusion, blockchain technology and cryptocurrencies have catalyzed a shift in financial systems, providing innovative opportunities that transcend traditional paradigms. Through decentralization, transparency, and the elimination of intermediaries, they are persistently redefining how transactions and financial services are conducted globally. Today, we've covered the foundational elements of blockchain, explored the rapid evolution of cryptocurrencies and DeFi, and understood the new landscape of opportunities and challenges in cryptocurrency trading. As we continue our journey to understand financial technologies, it will be essential to stay abreast of developments in regulations, technologies, and market dynamics that shape this extraordinary field. Thank you for joining today's session, and I hope you found this exploration of blockchain technology and cryptocurrencies enlightening. Quantum computing emerges as a transformative force, distinct from traditional classical computing in several fundamental ways. It harnesses the principles of quantum mechanics to process information in ways that classical computers cannot replicate. In the realm of finance, quantum computing holds tremendous potential, promising to revolutionize various aspects of financial analysis, risk management, and algorithmic trading. So far, we learned about the transformative impact of blockchain technology and cryptocurrencies on financial systems, including their decentralized nature and the importance of smart contracts. We explored how blockchain operates as a secure ledger for transactions and examined the rise of decentralized finance, DeFi services that democratize access to financial products. Additionally, we discussed the challenges of cryptocurrency trading, including market volatility and regulatory complexities. Today, we will cover quantum computing and its implications for the finance sector. In this section, we will explore a simple quantum circuit implemented using the Qiskit library, which demonstrates the fundamental concepts of qubits and superposition. First, we create a quantum circuit with a single qubit, which serves as the basic unit of quantum information. We then apply a Hadamard gate to our qubit. This crucial operation puts the qubit into a superposition state, meaning it can simultaneously represent a 0 and a 1, reflecting the unique behavior of quantum systems. Next, we measure the qubit, which collapses its state into one of the two possible outcomes, either 0 or 1. The measurement results will vary due to the probabilistic nature of quantum mechanics, showcasing different outcome counts when we execute the circuit multiple times. We run the circuit on a quantum simulator provided by Qiskit, which allows us to emulate quantum behavior on classical hardware. Finally, we print the results of the measurement, highlighting the inherent uncertainty and variability of quantum states. This basic example lays the groundwork for understanding how quantum computing could revolutionize complex financial computations. In this segment, we will delve into how to create a quantum approximate optimization algorithm, QAOA, circuit tailored for portfolio optimization. The function create_QAOA circuit begins by taking a graph representation of the problem and a specified depth for the QAOA algorithm. The number of qubits is determined based on the nodes in the graph, creating a quantum circuit with the corresponding size. Initially, each qubit is placed in a superposition state using Hadamard gates, allowing for a broad exploration of potential solutions. The heart of the QAOA consists of alternating layers, where we implement both the cost and mixing Hamiltonians. The cost operator, represented by control-X CNOT gates, captures the relationships defined by the edges of the graph, directly linking qubits to the problem constraints. Subsequently, the mixing operator applies rotation gates, Rx, to enhance the mixing of states, with the angle parameter gamma guiding the exploration. By executing this circuit, we can efficiently optimize our asset portfolio, leveraging the unique capabilities of quantum computing to achieve solutions faster than classical methods. In this section, we will explore a fundamental implementation of a Quantum Monte Carlo simulation using Qiskit, demonstrating how quantum circuits can be constructed for financial risk analysis. The function, Quantum Monte Carlo sim, begins by creating a quantum circuit that consists of 3 qubits, which is an appropriate choice for managing multiple scenarios simultaneously. Within the loop that runs for a specified number of simulations, it applies the Hadamard gate to each qubit. This gate is crucial as it prepares the qubits into a state of superposition, allowing them to represent multiple states at once. Such manipulation of states is what gives quantum computing its advantage in evaluating various risk parameters effectively and efficiently. Following the initialization of the Hadamard gates, the circuit is then transpiled. Transpilation is a process where the quantum circuit is optimized for a chosen backend, ensuring that the execution is efficient. Here, the circuit is tailored to utilize basis gates like U3 and CX, which are essential for quantum operations. The transpiled circuit is returned, ready for subsequent simulations that can lead to faster and more accurate risk assessments when analyzing investment portfolios. In this section, we'll explore the construction of a basic quantum support vector machine, QSVM circuit using Qiskit, which is pivotal for enhancing trading strategies through improved classification of market trends. The function begins by defining a feature map using the ZZ feature map, which is crucial for encoding classical data into a quantum circuit format. This feature map is designed to handle a specific dimension, aligning it with the length of the provided input data, allowing it to capture the necessary correlations. Following the creation of the feature map, we instantiate a quantum circuit initialized with the number of qubits corresponding to the feature map. Next, we encode the classical data into quantum states. This is achieved by iterating over each data point, appending the feature map while binding it to the parameters of the current data input. This step is essential as it transforms our classical inputs into formats suitable for quantum operations. Finally, a linea layer is appended to the circuit, which serves as the classification component. This layer is fundamental for decision-making, as it evaluates the encoded features for trend classification in the market. The resulting quantum circuit thus seeks to leverage quantum mechanical advantages to improve execution speed and accuracy in trading. In this section, we will delve into the implementation of a lattice-based encryption method designed to protect sensitive financial data against quantum attacks. The function begins by generating lattice vectors, which serve as the foundation for encoding the plaintext securely. These vectors are critical because they create a geometric structure that complicates attempts at decryption without the appropriate keys. Next, the coded function initializes an empty list called encoded text, which will store the encoded representations of the original plaintext. The core of the encoding process involves a loop that iterates through each lattice vector. For each vector, the function applies a specific encoding mechanism, denoted as encode-with-lattice, using the original plaintext and the current vector. This process transforms the plaintext into an encoded format that leverages the mathematical complexity of lattice structures, thus enhancing its security. Finally, the function returns the compiled list of encoded text, providing a robust method for securing data. This approach is vital for financial institutions as they maneuver through emerging threats in the wake of quantum computing advancements, ensuring that their data remains protected against potential quantum hacking threats. In conclusion, quantum computing is not just a futuristic concept, it is on the brink of changing finance as we know it. From optimizing portfolios and improving risk analysis to enhancing trading algorithms, the potential applications are vast and transformative. As we continue to explore this field, it's crucial to remain agile in adapting to new challenges and opportunities. So, as we wrap up this session, keep in mind the immense possibilities quantum computing holds. Just like blockchain and cryptocurrencies have shifted paradigms, quantum computing stands ready to do the same, ushering us into a new era of financial innovations. Thank you for joining me in this exploration, and I hope you're as excited as I am about what the future of finance holds.